So I'm also a third-year PhD student at the University of Leeds. My project's about the Karst hydrogeology of the chalk aquifer. The project's in partnership with Affinity Water, a water company, and the British Geological Survey. And with a slightly altered title, today I'm going to talk about investigating rapid groundwater flow in the chalk aquifer using trace tests specifically to public water supply abstractions. Okay, so I'll start by talking about the chalk aquifer a little bit in general and the importance of rapid groundwater flow through the aquifer. Then we'll have a look at some examples of karst geomorphology in my field area in Hertfordshire, and then move on to talk about why trace testing to public water supply wells is such a good method to study karst in the aquifer. And we'll have a look at some results and talk about some implications for groundwater protection. Okay, so the chalk aquifer is the most important groundwater resource in the UK. It's designated as a highly productive aquifer, and its extent is outlined on the map on the right-hand side. It supplies around 65% of public drinking water to the southeast of England, and around 30% in Greater London. And we also know that a component of flow through the aquifer is rapid, and we have evidence of this from rapid turbidity and contaminant responses to rainfall. And we also have more direct evidence from multiple field tests using artificial tracers that have repeatedly demonstrated flow rates from the surface to springs at greater than 5 kilometers a day. And this is really quick for groundwater. So groundwater flowing greater than about half a meter a day is considered fast, and it can be much, much slower than that. So 5 kilometers a day is really at the top end of the scale. Okay, so what kind of features can conduct flow through a body of rock at greater than 5 kilometers a day? Because even through a well-connected chalk fracture network, something like 30 meters a day is considered really fast. So larger voids are required. And these voids formed by dissolution are known as karst. And classic examples of karst landscapes with like large sinkholes and big cave systems characterising them can be found in areas like the Peak District in South Wales, where the bedrock is the Carboniferous limestone. In contrast, the two photos here show the kind of karst features that we see in the chalk. So on the left, the two red arrows point to conduits. And whilst there have been a few caves mapped in the chalk, conduits are generally the largest kind of void that we see. And they're the features that are responsible for conducting flow at these really high flow rates. They're generally sort of up to a meter in diameter and have a tubular to elliptical shape. And they nucleate and develop on harder layers in the aquifer where vertical flow is restricted. And then on the right-hand side, we can see some solutional features in a borehole wall. So this is a down borehole photograph. And these are probably related to a different kind of karst feature called a fissure. And fissures are basically fractures that have been enlarged by solutional processes. And these have more of a planar profile than conduits. And these are thought to be sort of pretty ubiquitous in the chalk. Okay, and we'll have a look at their role in the function of the aquifer now. So basically there are multiple flow regimes in the chalk and they all interact. But as stated in this 2001 BGS report on the chalk aquifer, without solution enhancement of the fractures, the high transmissivity of the chalk would be impossible. So essentially, without the influence of karst, the chalk wouldn't be the groundwater resource that it is. But sort of despite this appreciation of the importance of karst and fissures in particular, our characterization of flow through them does remain quite poor. Okay, So now we're going to focus in on flow entering karstic conduit systems from surface watercourses. These systems present a significant risk to water quality in the aquifer due to the rate at which they can conduct pollutants through the aquifer, because this severely limits natural attenuation processes that usually make aquifers quite good at attenuating contaminants such as chemical diffusion into the matrix and mechanical dispersion via multiple flow paths. So we'll have a look at some examples of this in the field area now. Okay, so my field area is in South Hertfordshire, just north of London, and it is probably the most studied area of the chalk for Karst, mainly because of this big swallowhole complex near a place appropriately named Water End. And in my field area, lots of streams flow off the impermeable London clay deposits, shown here in this grey colour, and onto the chalk. And as the stream water flows onto the chalk, the streams are slightly acidic. The stream water is slightly acidic as it meets the chalk, and we see a concentrated zone of karst development that lines this Paleogene deposit chalk contact, where the streams run over the contact. And this isn't just the case in Hertfordshire. This is the case across the chalk, where we see this relationship between the Paleogene and the chalk. And the features that are formed, generally known as swallow holes, are natural openings in the ground that take flow from surface streams, and they're connected to subsurface conduit systems of varying levels of development within the subsurface, so within the aquifer. But a very well-developed example can be found at Water End, shown on the map here. And this takes all the flow from a small river called the Mimshall Brook, apart from under flood conditions. And the lines demonstrate the rapid connections that have been established to sites across the Lee Valley to the northeast at distances over 18 kilometers. And these connections have been established over 3 studies, 2 of which were done in the early 20th century using trace testing methods. And these were some of the earliest trace tests done in the UK. So these were qualitative because they were very early trace tests. There's been one much more recent one, and this did a good job of establishing connections across the Lee Valley, but the sampling frequency was quite low as a result of the amount of monitoring sites that were included in the test. Okay, so let's have a look at some of the features. So this is an aerial shot and a map on the right-hand side of Water End. The map shows individual swallow holes within the area circled in red on the left-hand side. Essentially, the greater the flow, the more become active as the capacity of each swallow hole is reached. And then, interestingly, when the capacity of all of them is reached in flood conditions, Water End overflows to the west along the line of that dashed arrow in an overflow channel, and then southwest and joins the River Colne catchment. So as we saw in the previous map, water entering the aquifer at this point flows northeast into the Lee Valley into a different surface water catchment. So it's just a nice example of how karst can transfer flow between these surface water catchments. Okay, so this is one of the swallow holes at Water End, and sadly this is the state of quite a few of the features here and elsewhere in this area, and it's just a clear illustration of the vulnerability of the aquifer at these sites. Okay, so one more example. This is a sinking stream flowing off the London clay in the River Lee catchment. And so rather than an impressive set of swallow holes, flow along this stream sinks into the aquifer via multiple smaller openings in the stream bed, as can be seen on the two photos on the right hand side. And the location of these openings is really dynamic. Both of these, for example, opened in the sort of winter 2020-2021 period, just after I started my project. And over that period, another larger swallow hole that had been previously mapped to take most of the flow from the stream had silted up. Okay, so a few examples, but it's important to note that most, if not all, streams flowing off the Paleogene deposits are likely to lose flow to the chalk aquifer, either via sort of point source recharge through large open swallow holes, or more sort of diffuse infiltration over a reach on the chalk. Okay, so now we can take a look at a method of studying these karstic systems. So groundwater trace testing, just go through sort of a brief introduction of it here, is a method where we release a traceable substance, such as an artificial dye, into the aquifer, either via a swallow hole or a borehole, and monitor sites for the arrival of that tracer. And monitoring sites are usually natural discharge points in the aquifer, like springs, or, as we'll discuss a bit more in this talk, artificial discharge points like public water supply wells, from which groundwater is abstracted. So at its most simple, but potentially most powerful, what you do with a trace test is prove a connection between 2 points in the aquifer if you see tracer arrive at your monitoring site. Taking it a little bit further, a quantitative trace test is one where samples are taken at frequent intervals and analysed for the concentration of the tracer. And this delineates a tracer breakthrough curve, like we can see in the plot on the bottom right-hand side. And that's sort of two sort of quite classic shapes of a tracer breakthrough curve. And from plots like this, we can calculate the amount of tracer that has arrived at each monitoring site, if we have the discharge data for that monitoring site. And we can calculate the groundwater velocity, assuming flow is in a straight line from one point to the other. Obviously, this is a big assumption, but it still is a helpful comparison when comparing connections between sites. Okay, so the focus of testing so far from swallow holes has been to characterise flow to springs, and the results of the test shown here are pretty characteristic of what's been found. So rapid flow up around that sort of 5 kilometre a day mark, with a sort of moderate to low recovery of tracer. So actually 22% is quite a high recovery of tracer in the chalk, but there's still a significant amount of loss there. And we're also seeing these connections over quite long distances. So I think in this test it was around 5 kilometres, but we've seen connections well up over 18 kilometres. And so, yeah, the average flow velocity over the 27 proven flow paths is 4.8 kilometres a day. And just to reiterate, this is fast in groundwater, and for comparison, the straight line velocity in a trace test in the Sherwood sandstone in the north of England, from one borehole to another, was about 3 meters a day. And again, for the Sherwood sandstone, that was considered quite a considerable flow rate. And also another note here, compared to other chalk aquifers in Northern Europe, there's been relatively little trace testing done in the UK. You know, in the chalk aquifer in northern France, trace testing is a lot more commonplace. Okay, so what do these tests actually show? Well, they characterise flow through conduit systems, because as we release tracer into a natural inlet to a conduit system, and we monitor the natural outlet, a spring. But we know that not all the tracer makes it to the spring, so where does the rest of it go? And once leaving the natural preferential pathway, does it travel as fast, and is the attenuation greater in this area? And this is quite hard to study by just monitoring springs. So trace testing to public supply wells could be really useful in investigating these questions. And that's because a well is unlikely to lie on that natural preferential pathway and intersect a conduit network. But we already know that some of them especially are impacted by karst, probably via connectivity to well-connected fissures. This evidence comes from previous trace tests and also those other karstic indicators like spikes in turbidity following rainfall. Okay, so these kind of tests could provide a method to investigate karstic flow outside natural preferential pathways, from which we can think about contaminant transport and attenuation to sites outside these conduit networks. And from a more applied standpoint, they also provide empirical evidence for catchment management decisions like land use planning. Okay, so we did some quantitative trace tests to public water supply wells in Hertfordshire, and some of the abstractions that we tested, that we did trace test to, were really impacted by those indicators of rapid transport from the surface, like turbidity. Some were sort of moderately impacted and some weren't impacted at all. So there was a range. So let's have a look at the results. So the map here summarizes our testing from sinking streams. The solid arrows show established connections and the dashed arrow shows a previously established connection. Annoyingly, the landowner has changed since the last study was done, and we no longer have access to the spring, which is obviously quite frustrating, but we were able to monitor these abstractions shown on the map. So there's 5 of them there. So the first observation here, these breakthrough curves show the breakthroughs from the Catherine Bourne to, they're just example breakthrough curves, but from the Catherine Bourne to site 1 and water end to site 2. So the first observation is that we only observed tracer breakthrough at site 1 and 2. And both of these are very impacted by Karst based on those other indicators, again, like turbidity and coliform concentrations following rainfall. These sites also lie near to natural karst features. So site 1 lies near to water end, and site 2 lies relatively near to a large spring, Arkley Spring. And then the second observation is that at sites 1 and 2, the type of breakthrough curves that we see are really comparable to those you'd expect to see at a spring, with a sharp rising limb and a more shallow falling limb. Now, this may suggest that the transport dynamics of the tracer to these wells is comparable to the tracer transport that we see to springs, i.e. that the transfer is strongly advective through the aquifer. And of the other sites, so sites 3 and 5, these are the ones that show no obvious indication of a rapid connection to the surface. And so we didn't necessarily expect there to be a connection from these swallow holes. But especially in the case of site 5, this is interesting, given its proximity to Arkley Spring and the fact it lies in a river valley where we often see high transmissivity in aquifers and in chalk. Okay, and site 4 does actually have, say, a turbidity response following rainfall, suggesting that a surface link does exist, but just maybe not from these swallow holes. And there are lots of swallow holes in this area. Maybe it's connected to ones that look slightly further to the west. Okay. So this is just a simple conceptual model that presents a potential mode of transport from sinking streams to karstic abstraction wells. So in this model, the tracer pulse is in one well-developed conduit following the natural preferential pathway. And then when the pulse enters the zone of influence from the abstraction, some of the tracer flows into highly permeable, well-connected fissures towards the abstraction. And flow is still rapid through the fissure network near to the large conduits, but probably slightly slower than conduit flow directly to a spring. And also the tracer attenuation is likely to be, through this fissure network next to conduits, is likely to be greater than direct flow to spring through the conduit system. And this means it might make it hard to establish connections to abstractions that lie further from a conduit network, because the attenuation might take the tracer to below the limit of detection. Okay, so quickly just go through some implications for groundwater protection of karst in the chalk. Okay, so groundwater in the UK is protected by source protection zones, which are centred on public water supply abstractions and springs in some cases, in which high-risk land use activities are restricted. And a numerical modelling approach is favoured for the production of these models. So an SPZ1 delineates an area within which the pollutant to source transport time is 50 days or less. Therefore, any karstic connection from a sinking stream to an abstraction would probably sit well within this zone. But as shown in the conceptual model, the land around swallow holes is often not captured by any source protection zone, because numerical models don't necessarily account for that extreme flow velocity through these karstic systems, and the fact that karstic conduit systems may not align to the regional hydraulic gradient. So in areas of swallow hole development, it may be better for there to be sort of a combined empirical and numerical approach to allow for swallow hole catchments with proven connections to public water supplies to be designated as a source protection zone 1. And this has actually been implemented at Water End, around Water End. Another thing we could do is to start using time series analysis methods to sort of prove more statistically robust correlations between turbidity and rainfall. And this would help us to identify wells that are vulnerable to rapid flow from the surface. And then swallow holes with possible connections to these vulnerable wells could be investigated further by artificial trace testing potentially. Okay, so in conclusion, Karst is critical to chalk aquifer productivity. Karst development at the surface is concentrated along the London clay chalk contact. Trace tests 2 wells allow us to investigate karstic flow outside natural preferential pathways and can provide empirical evidence for catchment management. And we found that tracer transport dynamics to wells near karst features and to springs are comparable. So we get some really strong connections to these abstractions near natural karst features, and incorporating an empirical based approach to groundwater protection is important to manage the risk from karst. Okay, thank you very much.